Hello and welcome back to the channel. Today we're going to explore the fascinating world of algebraic structures, specifically focusing on semigroups, monoids, and groups. Let's begin with the concept of a semigroup. A semigroup is an algebraic structure consisting of a non-empty set S together with a binary operation star such that it satisfies two key properties. First, closure. For all A, B belonging to S, A star B also belongs to S. This means that when we combine any two elements from our set using our operation, the result is still in the set. Second, associativity. For all A, B, C belonging to S, the expression A star B star C equals A star the quantity B star C. In other words, it doesn't matter how we group the operations, the result is the same. It's important to note that a semigroup does not require an identity element or inverses. Let me give you a concrete example. Let S equal the natural numbers n, with operation star equal to addition. For closure, A plus B belongs to the natural numbers for all A, B belonging to the natural numbers. For associativity, the quantity A plus B plus C equals A plus the quantity B plus C. Thus, the natural numbers under addition form a semigroup. Now let's move to monoids. A monoid is a semigroup that also includes an identity element E such that for all A belonging to M, E star A equals A star E equals A. The identity element is special because when we combine it with any other element, that element remains unchanged. So, a monoid satisfies three properties: closure, associativity, and the existence of an identity element. For example, let M equal n sub 0, which is the set containing 0, 1, 2, 3, and so on, under addition. The identity element is 0, since 0 plus A equals A plus 0 equals A for all A belonging to M. Therefore, n sub 0 under addition is a monoid. A group is a monoid in which every element has an inverse. Formally, a set G with binary operation star is a group if it satisfies four properties. First, closure. A star B belongs to G for all A, B belonging to G. Second, associativity. The quantity A star B star C equals A star the quantity B star C. Third, identity. There exists an element E belonging to G such that A star E equals E star A equals A for all A belonging to G. Fourth, inverses. For each A belonging to G, there exists A inverse belonging to G such that A star A inverse equals A inverse star A equals E. Let me illustrate with an example. Let G equal Z, the set of integers under addition. For closure, A plus B belongs to the integers. For associativity, the quantity A plus B plus C equals A plus the quantity B plus C. For identity, we have 0, since A plus 0 equals 0 plus A equals A. For inverses, for each A belonging to the integers, its inverse is negative A, as A plus negative A equals 0. Hence, the integers under addition form a group. Now let's discuss two important uniqueness theorems. Uniqueness of identity element. In any group G with operation star, the identity element is unique. Here's the proof. Assume E sub 1 and E sub 2 are two identity elements. Then E sub 1 star E sub 2 equals E sub 2 since E sub 1 is an identity, and E sub 1 star E sub 2 equals E sub 1 since E sub 2 is an identity. Therefore, E sub 1 equals E sub 2. So, the identity element must be unique. Uniqueness of inverses. Every element in a group has a unique inverse. The proof goes as follows. Let A belong to G, and assume B and C are both inverses of A. This means A star B equals B star A equals E, and A star C equals C star A equals E. Then B equals B star E equals B star the quantity A star C equals the quantity B star A star C equals E star C equals C. Therefore, B equals C. So, the inverse of any element is unique. A homomorphism is a structure-preserving function between groups. Let G with operation star and H with operation dot be two groups. A function f from G to H is called a homomorphism if f of the quantity A star B equals f of A dot f of B for all A, B belonging to G. This means the group operation is preserved under the mapping. For example, let f from Z to Z sub n be defined by f of x equals x modulo n. Then f of the quantity A plus B equals the quantity A plus B modulo n equals f of A plus f of B modulo n. So f is a homomorphism from the integers under addition to Z sub n under addition. An isomorphism is a bijective homomorphism between two groups. Let f from G to H be a function such that f is bijective, that is, 1 to 1 and on to, and f of the quantity A star B equals f of A dot f of B for all A, B belonging to G. Then G is isomorphic to H, meaning the groups are structurally identical. For example, let G equal the positive real numbers under multiplication and H equal the real numbers under addition. Define f of x equals the natural logarithm of x. Then f of x times y equals the natural logarithm of x times y equals the natural logarithm of x plus the natural logarithm of y equals f of x plus f of y. So f is a homomorphism. It is also bijective. Hence, it's an isomorphism. A subgroup H of a group G is a non-empty subset of G that itself forms a group under the operation of G. We write H is less than or equal to G to denote that H is a subgroup of G. The subgroup test tells us that a non-empty subset H contained in G is a subgroup if it satisfies two conditions. First, closure. For all A, B belonging to H, A star B belongs to H. Second, inverses. For all A belonging to H, A inverse belongs to H. These two conditions are sufficient when associativity and identity are inherited from G. For example, let G equal the integers Z, and define H equal 2Z, which is the set of all even integers. For closure, the sum of two even integers is even. For inverses, if A belongs to 2Z, then negative A also belongs to 2Z. So H is a subgroup of Z. Let G be a group and H a subgroup of G. Let A belong to G. The left coset of H with respect to A is H, which equals the set of all A star H where H belongs to H. The right coset of H with respect to A is HA, which equals the set of all H star A where H belongs to H. Note that in abelian groups, left and right cosets are the same. In general non-abelian groups, they can differ. Key properties of cosets include: cosets partition the group, two left cosets are either disjoint or identical, and the number of elements in each coset equals the number of elements in H. For example, let G equal the integers Z, and H equal 3Z. Then the left cosets are 0 plus H, which contains all multiples of 3, 1 plus H, which contains all numbers of the form 3k plus 1, and 2 plus H, which contains all numbers of the form 3k plus 2. Lagrange's theorem states that if G is a finite group and H is a subgroup of G, then the order of H divides the order of G, and the index of H in G equals the order of G divided by the order of H. Here, the order of G is the number of elements in the group, the order of H is the number of elements in the subgroup, and the index of H in G is the number of distinct left cosets of H in G. The intuition is that a group can be built from non-overlapping cosets of its subgroup, and each coset has the same number of elements as the subgroup. For example, let G equal Z sub 6, which is the set containing 0, 1, 2, 3, 4, 5, and H equal the set containing 0, 3. The order of G is 6, the order of H is 2, so there are 6 divided by 2 equals 3 cosets. These cosets are 0 plus H containing 0 and 3, 1 plus H containing 1 and 4, and 2 plus H containing 2 and 5. A permutation of a set S is a bijective function f from S to S. The set of all permutations of a finite set S of n elements forms a group under composition, called the symmetric group, denoted S sub n. The order of S sub n is n factorial. For example, Let S equal the set containing 1, 2, 3. Then S sub 3 includes the permutations, the identity which maps each element to itself, transpositions like 1, 2 which swaps 1 and 2, and 3 cycles like 1, 2, 3 which maps 1 to 2, 2 to 3, and 3 to 1. Cayley's theorem states that every group G is isomorphic to a subgroup of the symmetric group S sub G, that is, the group of permutations on the set G. The intuition is that any group can be represented as permutations of its own elements. This theorem guarantees that every group is a group of transformations. A subgroup N that is a subgroup of G is called a normal subgroup. Written N is a normal subgroup of G, if for all G belonging to G, Gn G inverse is contained in N. Equivalently, Gn G inverse equals N, or G star N star G inverse belongs to N for all N belonging to N. This ensures left and right cosets of N in G are the same. Here, Gn G inverse equals the set of all G star N star G inverse where N belongs to N. For example, in the integers Z, all subgroups Nz are normal since Z is abelian. In abelian groups, every subgroup is normal. Let G be a group and N be a normal subgroup of G. The quotient group G divided by N is the set of cosets of N in G, with group operation defined as the quantity A n times the quantity B n equals the quantity A b times n. The structure includes: the elements of G divided by N are the cosets Gn for all G belonging to G, the identity is En which equals N, and the inverse of Gn is G inverse N. For example, let G equal the integers Z and N equal 3Z. Then Z divided by 3Z is isomorphic to Z sub 3, which equals the set containing 0, 1, 2. Group theory provides a foundational backbone in the field of error detection and correction in digital communication. In linear block codes, codewords form additive subgroups of F sub 2 to the power n, the vector space of binary strings of length n. Operations in coding often use group structure, including closure under addition. In cyclic codes, subsets of F sub 2 of x divided by the quantity x to the power n-1 form a group under polynomial addition. Group properties enable the design of efficient encoders and decoders. In Hamming codes, the set of all valid Hamming codewords forms a group under bitwise XOR. Group structure allows for syndrome decoding techniques. Finally, in group-theoretic cryptography, concepts like permutation groups and cyclic groups are core to OSA, Diffie-Hellman, and elliptic curve cryptography. This concludes our introduction to group theory. These algebraic structures form the foundation for many advanced topics in mathematics and computer science. I encourage you to work through additional examples to solidify your understanding of these concepts. That's a wrap. Thank you for watching this video. Don't forget to give it a like, share with your friends and subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.